Thanks, Nick. Thanks for the introduction. Let me just make sure I have this. Okay, we're good. Okay, so again, my name is Mike Kiefer, and coming from Michigan State and University, and again, this is going to be. Actually, before I go ahead, I just want to acknowledge the long list of co-authors here. This was really a collaborative project that took place over the course of several years. And so this is the outline for this talk. So it's two parts. The first part is going to be a review of dispersion modeling, mainly going over the different types of smoke dispersion model and why you might choose one model versus the other, advantages and disadvantages. And then the second part is going to be an in-depth example, where we're going to dig into a case. And in this case, it's actually a pair of prescribed fires that were conducted in the Pine Barrens of New Jersey back in 2011 and 2012. I'll introduce the particular models that were used in the study, and then I'm going to show some results from some simulations, simulations of the two prescribed fire events, to really show how smoke dispersion models are applied to wildland fire cases, how they're validated, and then how they help researchers better understand the processes that influence smoke dispersion from wildland fires, which hopefully can lead to better predictions at these scales. And finally, I'll summarize and conclude and take any questions as time allows. So this is kind of the outline for the smoke dispersion model review. And before I proceed, I really want to acknowledge that the material for this review section really came from, at least was inspired by this review paper back in 2013, Scott Goodrick and company, Modeling Smoke Transport from Wildland Fires review. This is just going to be kind of a quick hitting review, and if you have a deep desire to learn more about smoke dispersion modeling, this is the paper you're going to want to go to. It's an IJWF back in 2013. But in this talk, we're going to go through 5 different classes of smoke dispersion models, starting with the simplest models, box models, Gaussian plume and Gaussian puff models, and those are also on the simpler end of the spectrum of smoke dispersion models. And then on to Lagrangian particle models and Eulerian grid models. I hope your eyes aren't glazing over at this point. This is a lot of fun terms here, but we'll get into each one of these. And the idea being that as you go from top to bottom, you have the box models simplest, require the least amount of information, but have the most limiting assumptions and the most limited applicability, to where the particle and grid models are really the more sophisticated models. They take more input, more information, but depending on what information you're putting in, you get more accurate results, and you have fewer limitations and assumptions. So, but to back up just a second, what are dispersion models and what are they used for? Well, they're models that simulate the transport and dispersion of smoke, or actually pollutants, atmospheric pollutants, from one or more sources. And they're used for, and this is not an exhaustive list, but air quality, I have here fire management decisions, pollen dispersal predictions, and they vary widely in terms of complexity, as you'll see as we go through these few slides ahead. And the choice of model, one versus the other, is going to be problem dependent. And the following is a brief review of dispersion model classes. So we're going to start. It looks like it's trying to update Windows. Thank you. Okay, good. On with the show. So what are box models? Box models are the simplest type of dispersion model, and they basically assume that smoke fills a box representing an airshed. And typically that's going to be a confined basin or valley. So this could be hundreds of kilometers across, and the depth of that box is going to be basically the mixed layer, or the layer in which constituents in the atmosphere are mixed during the daytime heating. That's going to be, so you're talking about these are large boxes, and concentrations of pollutants within the box vary with time as smoke enters or leaves the box. And there are a couple of assumptions. The first assumption is that dispersion is instantaneous. Now, I don't mean that at 10 o'clock there's no smoke, and at 1 second later it's filled the box. We have to understand that these kinds of models are applied on multi-day time scale, so 1 or more days time scale. And on that time scale, the assumption that when smoke enters the box, it's immediately mixed across is reasonable on those time scales. The other assumption is that you're not looking at individual sources. You're not saying there's a fire here, smokestack, this power plant emissions. you're basically just distributing the source across the bottom of the box. But what this takes as inputs in terms of weather are mixing height and transport wind. Mixing height defines the top of the box, how deep the box is, and then transport wind to figure out the pollutants entering and exiting the box. So very little information goes into these models, but they have limited applicability in terms of if you want to know what's going on a few kilometers away on short time scales. This is not the model for you. This is the model if you want to know what the concentrations are going to look like over the next several days as you have large multi-source events. Then the next step is the Gaussian plume models. Gaussian plume models predict the dispersion of a point or area source of pollutants, whether it's elevated as in a smokestack or point, or surface, as in, for instance, a surface fire. They use fewer assumptions than box models. For instance, the dispersion is not instantaneous, so you can apply this on smaller time scales. You're not looking at what's going on over the next few days. You can apply this on a shorter time scale, as in hours into the future. And the source is not distributed across the airshed, as I said right here in the first bullet. It can be a point source. It could be an aerial source, unlike a box model where it's just like the whole valley is the source. The bottom of the valley is the source. Gaussian here is the big assumption. What does Gaussian mean? It refers to the assumption of a Gaussian probability distribution of the pollutant in the cross-plume direction, which is a lot of words, but basically this is foul box, or V-smoke. This is just a particular Gaussian plume model. And what this is concentration along the axis of a smoke plume. And as you go away from the source, the concentrations reduce due to dispersion. But if you were to cut right across the plume, in that cross-plume direction, and you looked at where are the highest concentrations, where are the lowest concentrations, the distribution would look like this on the right, where you have the highest concentrations at the center, and it decays. Basically, it's a bell curve as you move away. As mixing processes are strongest on the edges, you're entraining that fresh air into the plume most readily on the edges of the plume. So again, you're not actually resolving the actual dispersion of pollutants. You're representing it in a relatively simple way, but under some conditions, that is actually an applicable assumption. Meteorological inputs, transport wind, again, either mixing height or atmospheric stability, because with these models, with this level of this type of model, you're not actually resolving the plume right above its source. So you need to know, in the plume is, in the case of a fire, buoyant, the pollutant, the air is buoyant above. So you have to figure through what depth of the atmosphere are the pollutants to be released before you allow the wind to carry them away. So you need more information with a Gaussian plume than compared to a box model. But the big assumption is there's no variation in time and space. So you have a single weather observation that represents an entire area, and it doesn't vary with time. It's fixed, so it's one observation. An example, like I said here, is V-smoke. V-smoke is an example of a Gaussian plume model. Gaussian puff models, they're similar to plume models in that when you look in the cross-plume direction, the distribution is Gaussian. It's strongest at the center. The concentrations are highest at the center and decay as following the Gaussian distribution as you move away from the center. However, unlike a plume model, with a puff model, it's exactly what it sounds like. You're releasing the pollutant in a series of puffs. So rather than just a continuous release like a plume model, these are puffs. You're releasing these puffs. And these puffs are going to grow with time as air is entrained into these puffs. As air is mixed into the puffs are going to grow with time, representing the dispersion process. But the big difference between a plume and a puff, in addition to the fact that the emissions are released in puffs rather than continuous, is that the weather conditions can actually vary in time and space. So you're no longer just using a point observation. It's not fixed in time. It can vary with time. It can vary in space. So you imagine you release a puff. Initially, it's transported off to the northeast. The puff is growing in size as air is mixed into that puff. It's moving off to the northeast. But perhaps at some later point in time, as it's moving northeast of the source, the winds are coming around more to the west and to the northwest. And so the puff, as it continues to grow in time, as air is mixing into that puff, it's moving around. Unlike a plume, where you're just looking at a cone downwind of the source, and that cone doesn't change with time, and it's not sensitive to what might be going on away from the source in terms of the weather conditions. Two examples of Gaussian puff models, high split and cow puff, and I have a little star here, a little asterisk. to indicate that high split is a hybrid model and that it can take on, part of it, the dispersion is dealt with via these puffs, and the other part is as a particle model. What is a Lagrangian particle model? This is our next class of model. And in particle models, the plume is represented as a collection of particles. So you're not dealing with just releasing a puff, or you're just assuming a steady emission or emissions from the bottom. You're actually releasing, it can be as many, hundreds of thousands or even greater number than that, particles. And these particles are very, very small, but they contain a fixed massive pollutant. And those individual particles are moved around by the mean and turbulent component of the wind. So the mean wind, average wind might be northwest at 10 miles an hour. That's where the particles are moving. But there's a turbulent component. So these particles are moving in a random fashion as a result of the turbulent part of the wind field. And to compute concentration, you can construct a volume and count the number of particles in the volume. And since you know the mass of each particle, you can figure out what the concentration of that pollutant is. Like puff models, particle models use what is known as a Lagrangian or moving reference frame. That's what the Lagrangian means. Your reference frame is with the wind, so you're tracking the individual particle or the puff, and you're following it along its path and keeping track of what's going on to that puff or that particle. That's what the Lagrangian means. However, unlike a puff model where we assumed that the puff is growing in size with time as air is entrained in, and if you cut through the puff, you have the highest concentration at the center and it drops off like a bell curve. With a particle model, diffusion and entrainment are actually resolved because it's the result of those particles as they're spread apart. These particles go this way, those particles go that way, and you're actually resolving the dispersion of the pollutant via the particles themselves. Again, an example is high split. Again, like I said, puff and particle. Flexpart, and that's the model, actually, as we delve into an example, Flexpart is the model that I personally use. Day smoke and PBP are other examples of particle models. And the last type of model is an Eulerian grid model. And Eulerian grid models represent the atmosphere using, well, a grid. And it's a grid similar to those used in the weather models. Weather models, when you see your weather forecast, those are based on weather models, computer models, and most computer models are using a grid system. And what these are just basically a collection of interconnected box models. So with a box model, you might have hundreds of kilometers on, east, west, north, south, maybe 2 kilometers deep. Here, you're shrinking those boxes down to a lot smaller. It could be something on the order of 10 kilometers, 20 kilometers on a side, maybe 100 meters deep. And each one of those boxes, as smoke enters the box, it moves in between these interconnected boxes. They all communicate with each other. That's what these cells are, these grid cells. A grid model can, like I said, can be thought of as an interconnected box model. Eulerian models are well suited to the modeling of chemical transformations, for instance, the production of ozone, the formation of ozone, because of that regular grid. It just basically makes those calculations more straightforward. But Eulerian grid models, they span a wide range in scales in terms of what they're able what they're used for. An example of a model that might be used on a larger scale is CMAC, where you might have multiple sources of different kinds all around you might be looking at ozone concentration. In this case, this is the concentration of ozone on a particular day in 2013, June 2013. And you're looking at ozone concentration across the country from perhaps multiple sources, different sources in terms of, you might have fires, you might have smokestack, you might have power, you might have transportation system, automobile traffic, and you're looking at a large area. You don't care what's going on right above the source. You're not focused on what is going on with the concentration of this pollutant right above where it's released. You're interested in a larger scale, bigger picture, what's going to happen what's going to go on in the next hours to days into the future across this large area. Aetham is an example where you take one of the grids like it's CMAC, where CMAC might be using a grid on the order of, say, 5 kilometers by 5 kilometers or larger. You shrink it down to maybe where it's just a few tens of meters on a side, and you're actually able to resolve the plume. For instance, you could actually resolve the smoke plume right above the fire. And that's what this is showing. This is showing, I believe this is showing the concentration of the pollutant within, actually this might be, I think it's color-coded by elevation. But what the idea here is this is a smoke plume above a particular fire using Aetham. And here you're really wanting to know what's going on with that plume, what's going on right in the vicinity, you're able to study the dynamics, the physical processes within these plumes, whereas CMAC, you don't really care about the individual plumes, you're interested in the bigger picture. So this is part 2, this is my in-depth example, and what we're going to do here is look at an application of a dispersion model to a couple of prescribed fire cases. And the modeling approach here is to take a Lagrangian particle dispersion model, and the one I've used is Flexpart Work, and I'll talk about what that is in a moment, with the weather information, the meteorological fields provided by an atmospheric model that contains both a fire heat source, so I know, and we have information about the buoyancy of the plume above the fire, but we also have a resolved forest canopy, so I'm actually able to resolve the atmosphere within a forest canopy as well as outside the forest canopy. And the goal of the study, the 2 goals of the study, first of all, validate the Flexpart Work smoke simulations. And second, use the model as a tool to examine the impact of the forest canopy on the smoke plume to hopefully better understand the processes and hopefully make better predictions at these small scales. So what this is just an overview of the New Jersey pine burns. And what we have here is a map on the upper left corner of the slide. You have central and southern New Jersey, and you have the pine barrens of New Jersey. And this little red inset shows, this is a Google Earth map. There were 2 burns that were conducted. The burn in 2011, that was March 20th, 2011, that was a 265-acre burn block. And the March 6th, 2012 case, that was a 240-acre burn block. And these were conducted as part of a JFSP field campaign to collect weather observations and smoke measurements in order to validate the weather models and the smoke dispersion models that were as part of this study. And I mentioned here vertical heat fluxes to emphasize that these were low-intensity fires, but the 2011 case was considerably stronger in terms of the intensity of the fire, greater heat output from the 2011 fire compared to the 2012 fire. And these photographs on the left side of the slide just illustrate what the smoke plumes look like at different in these 2 cases, and to mention that these were mixed scrub oak and pitch pine forests, and it was almost entirely surface fire. There was very little crowning that took place. So these are some of the instrumentation that were used as part of this field campaign. For the smoke dispersion model validation part, there were PM 2.5 monitors, so these are measuring a particulate matter 2.5 microns or smaller. These were set up, four monitors were set up in 2011, 4 monitors were also set up in 2012. They happen to be in a better position with respect to the actual conditions on that day in 2012. So 2011, only 2 of the monitors actually sensed the smoke plume. But in 2012, it was a better setup in terms of, what actually ended up happening in terms of the smoke plume direction. Ceilometer in 2012, what that gives us is estimates of plume height and also concentrations within the boundary layer. But that was only in place for 2012, that was not in place for 2011. And then I mentioned here that there was an atmospheric model validation component, and so we had these towers, these instrumented towers, measuring a number of things, wind speed, able to compute turbulence from that. We have moisture, we have net radiation at different levels within the vertical profile above the fire, or in the vicinity of the fire. So we have that, and the model was validated. The weather model that was used in the study was validated in this 2014 paper in the Journal of Applied Meteorology and Climatology. So I mentioned ARPS canopy on a previous slide. What it is that at its core, it's something called the Advanced Regional Prediction System, or ARPS model. And it's a weather model that's suitable for prediction at multiple scales. So it can be applied at continental scales, can also be applied down at the scale of forest canopies. Its original focus was actually on thunderstorms, understanding thunderstorms. The canopy part of ARPS comes in via this canopy model that accounts for things like canopy drag, turbulence dissipation in the canopy, moisture exchange, heat exchange with the atmosphere. So you have these processes that are represented in the model, and they're represented differently than the ARPS model, the standard ARPS, or most weather models, in that most weather models you have basically one layer in which you're dealing with all of these processes that are going on between the forest canopy and the overlying atmosphere, the heat exchange, the moisture exchange, drag of the vegetation on the wind. That's all dealt with in a single layer. Whereas in ARPS canopy, you actually have multiple layers, you can have as many as you desire within the forest canopy. That's really the advantage of ARP's canopy, and it was used in this study because of the fact that with these low-intensity fires, smoke tends to linger in the vicinity of the burn, tends to linger within the forest canopy, and what's going on with turbulence, with the wind field inside the canopy is of paramount interest. And the fire here in this model was parameterized as an area of vertical heat flux. And it's not like FireTech, WFTS, WRF-S fire, if you're familiar with those 5 models. You're just basically representing the fire as a heat source that perturbs the overlying atmosphere, but it doesn't feed back on the fire itself. Flexpart Work, like I mentioned, Flexpart is a Lagrangian model used for global weather models. It was suitable for simulating smoke transport and dispersion on continental to global scales, but the Flexpart Work is a version of Flexpart designed for use with the weather research and forecasting model, which is the model that's really behind most of your weather forecasts that you see on any given day. Most of our weather models used in the US are actually based on the Work. And Flexpart Work is able to simulate smoke transport and dispersion even down to local scales within, say, kilometers of the source. And basically, we're able to take ARP's canopy output, that weather model output, ARP's canopy, and feed it right into Flexpart Work to move the particles around. This is just to give you a little idea of the numerical design of these experiments. We're representing the forest canopy using LiDAR data, LiDAR-based plant area density data. So we know where the canopy is more dense, we know where there are gaps, and so there's some real ground truth that's going into ARP's canopy to tell us where the forest canopy is, where it's more dense. Again, the fire is that area of surface heat flux. This is the burn unit pattern in the ARP's canopy model. This is 2011. What these orange cells are the fire at a given point in time. And the fire is coded to work its way through the burn unit with the timing of that based on the observations from the field campaign. And the output from the ARP's canopy simulations, they're ingested into Flexpart Work, and they move those particles around. You have the mean, you have the turbulent wind, and that's moving those particles around, and we're actually resolving the smoke dispersion both within and above the forest canopy. So this is the first one thing I want to talk about is the model validation. How do we validate the model? This is one example, and it's how we evaluated the plume height within Flexpart Work. So the challenge here is that there's no standard method for deriving plume height from dispersion model output. And what we have here is this is output from the Flexpart model at one point in time, and each gray dot here represents a particle. And there's a total of I think this is something on the order of 100,000 particles that are released during this event. And at this time, this is what the smoke plume looks like, and it's represented by the collection of these particles. You can look at that and say, well, your plume height's about 1.5 kilometers, or your plume height is this tall, this deep of a plume height. Well, we need an objective way to come up with a plume height to compare to the plume height from the ceilometer. And so what was done is at each level in the atmosphere, you start at the surface, you calculate, you look throughout the model domain, you look for where the maximum concentration is, and that's assumed to be at the center of the plume. And you do that at each of the vertical levels as you go up through the atmosphere, and you get a profile like this, which is the concentration of the PM2.5 within the plume as you move along the axis of the plume. And where the concentration was reduced to 20 micrograms per cubic meter, which I realize sounds quite arbitrary, but where that decreases to 20 micrograms per cubic meter is defined as the plume height. And that threshold was actually based on a very close examination of the ceilometer data. So we're able to say that anything smaller than 20 micrograms per cubic meter is just background. Because there's particulate matter even, obviously without the fire, and that's the particulate matter without the fire. So when the 20, anything greater than 20 is basically within the plume. And so this is our time series. You have the blue as the ceilometer, so you have rises and falls. You have greater variation in terms of the plume height within the observations compared to the model. The model is smoother. That's a common result from models. But overall, it has the trends. It has the right trend in terms of the overall growth of the plume height and the overall maximum plume height. This is one thing I just want to mention before I wrap up and go to conclusions, is to say that the dispersion model here has been used to examine the sensitivity of the near-surface smoke plume to that forest canopy presence. So what we have here is this greenish, bluish color here, this turquoise color, represents the burn unit. The orange is where the fire is placed in the model. This happens to be a 1:12 in the afternoon for a 2011 case, and for the 2012 case it's 1:47. So it's basically early afternoon. And these are all the particles within a few kilometers of the burn unit, and they're color-coded by their height above the ground. Anything gray is above the canopy. Anything green is below the top of the canopy, but it's right, and anything black is right in the lowest 2 meters of the surface, so basically right near the ground. And what we can do by comparing simulations both with the canopy and a simulation where we totally removed the canopy, what we find is that when the forest canopy is present, the plume is actually more upright right above the fire. So the plume is more upright when the forest canopy is present, and that's true for both 2011 and 2012. So the particles are obviously right above the fire, very buoyant, they're surging upward. They move more vertically than horizontally after they're released when the forest canopy is present. And when the forest canopy is taken out, they're less buoyant, and they tend to move more horizontally before they start to ascend up and away from the surface. So we're able to use this dispersion model to help us understand some of the processes that go on within the forest canopy. So dispersion models, they vary greatly in complexity, from the very simple box models to the more sophisticated grid and particle models. This particular example shows how one smoke dispersion model is validated and how it can be utilized to better understand these processes. And hopefully what's coming out of this is that it improves our understanding of smoke from fires in forested land. So improving our understanding of smoke from fires in these forested landscapes helps us to make hopefully better predictions at these smaller scales. And so what I would end with is which model you choose is going to depend upon your scale of interest, local, days or minutes, and the degree of accuracy you need. If you're interested in biomass burning, what the effect of it is on particulate concentration in a large valley, you could use a box model like ValBox, as simple as it is. It gives you can give you what you need for that circumstance. If you're interested in the effect of Canadian wildfires and air quality in the Northeast U.S., an Eulerian model like CMAC, that'll work. That can be just what you need. But if you're interested in will the prescribed burn you're planning smoke out a nearby community, a Lagrangian particle model like Flexpart Work coupled to a canopy resolving weather model may be just what you need for that particular circumstance. And so with that, I'll say thank you, and I think I'm out of time.